La 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 la. All right, guys. How did I get that stuff? Mrs. Regan. Sneaking into Mrs. Christensen. How did I get the stuff in red? Why did I say cross down was a good bit of conversation that I heard? I multiplied? 1 times A plus 4 times C equals, but how did I get the equals?
Because that's the formula for an inverse.
That's the formula. Well,
I mean, that's how every inverse is.
this is the property or the characteristic of every inverse, that a matrix times another matrix is the identity. But how was I able to say that 1A plus 4C equals 1? The position. Does that make sense?
Oh, yeah.
And then cross over down. 1B plus 4D is equal to... Got it. You see it? Well, no. Well, yesterday at the end of class, I did write this. But how did I write this statement from this question? Any matrix times an inverse, we're trying to find the inverse, always makes, this is what we learned yesterday, any matrix times its inverse makes the identity. So I used, not necessarily, they didn't tell me like, hey, set up an equation, and then, but I used what I knew about the word inverse. And the word inverse says, any matrix times its inverse, any inverse times its matrix has to be the identity. Is that cool? So I used the definition of an inverse. I made my own little baby equation and said, I don't know the inverse, but all right, he has to be the same size. He's an A, B, C, D. And I'm going to find him. So I kept on going with negative A minus 3C must be 0 and negative B minus 3D must be 1. And then why did I say a couple times, as you guys were pondering at the beginning of class, solve for AC and BD instead of A, B, C, D? How can you solve for AC? System of equations. And how can you solve for BD? System of equations. Now, could you use substitution? Of course. But, guys, can you look at it and be like, oh, but what's way simpler than substitution? Elimination, because check it. In this case, maybe not always, but in this case, don't we have A minus A ready to go? And in this case, don't we have B minus B ready to go? Because of the numbers, it doesn't always work that way, but these ones are ready to go. So what statement will we get when we add down over here? Good. C is equal to? Got him. If C equals 1, can't I do some back substituting and say, okay, then fine, A plus 4 times 1 is equal to 1, plugging back in to either one. I just chose the one with pluses. I like it better than minuses. But you guys do you. A equals? I solved for CA, I guess. Maybe I should have even said it weirder, but I figured solving for AC, at least in your brains, would like, hey, somehow they go together. And solving for BD. Okay, adding over here. What statement do I get? D equals 1. Good. And then back substitute again. B plus 4 times D is equal to 0. So B equals... Got him. We're done, right? Well, kind of. We just have to put all the pieces together, because what did they ask us to find? The inverse of A. You guys have seen that notation again, right? Matrix A inverse is... Can't I take my A and B and C and D and plug and chug it to the right spots? So I have my A is negative 3. I have my B is negative 4. I have my C, which is 1, and my D, which is 1. There we go. Now some of you might be pondering and looking and being like, huh, man, that looks similar to the first matrix. Just kind of like there were some rearrangements, sort of. What do you guys notice about how this compares to the original? Now be careful, I'm not going to say something like always true, but it looks awfully similar. I wonder if we could find a pattern of formula. Matthew, what do you see?
I see that B and C are switched, change your name. And for A and B, you switch the signs. Like, no, I
Close.
have it backwards.
Yeah, say it the other way. Good.
And you switch the signs for
Good. So switching, when Matthew's saying switched, he's saying the entire terms. Do you guys see that 1 and -3 literally switched? But then the 4 was still in the 4 spot, but what happened to its sign? Switched signs, and then what happened? Oh. So it seems like there's patterns on the diagonals. The main diagonal seems as though the terms will switch, and the opposite diagonal seems as though just the signs switch. Huh. I wonder if that's a thing. Real quick, how could we make sure that we were right? Yeah, you could go ahead and do A times A inverse like we did yesterday, and what would happen? You would get the identity. But since we did it all together, I think you guys were double checking my work along the way, yeah?
Yes.
I think we're all right. Let's go ahead and move on. Let me give you a moment. If you remember yesterday, I said that we were going to not only learn what an inverse matrix is, we did that yesterday. It's a matrix such that the multiplication undoes all of the terms down to the identity. But I also mentioned that we would see different ways of finding the inverse. But I also gave a hint that little baby 2x2s have the most options. Little baby 2x2s have the most options as far as how to find an inverse. But sadly, the bigger you get, 3x3, 4x4, the fewer the options. I'm going to have you guys write this page, and as you do, I'm going to write up a 3x3 up here. I should grab my calculator. I need to make sure this 3x3 I'm making up is even invertible. There's a trick to doing that. You'll learn it by the end of today. Invertible. Oh, that's also not singular. Okay. By the end of this chapter, there will be a time, a very brief time, but a time, where you're going to be making up your own square matrices for a type of problem. And in order to make up your own matrix, you're going to need to make sure it's invertible, or that the inverse exists. Otherwise, well, it'll be impossible to break your code. Ooh, that sounds exciting. It'll be impossible to break your code. So it is important to not only be able to make a matrix, but to make a matrix whose inverse exists. Once again, we'll learn that, how we can tell. Square isn't enough for the inverse to exist. We'll learn that by the end of today, but stink. I just made one that has a really nasty inverse. Let me try to make one that doesn't have as nasty of an inverse. Let's see if this one's any better. Are you any better? A little bit nicer. Not much nicer, though. Okay. We'll just keep it here. It is invertible. It's not a nice one. Before we talk about this page, hey guys, what if I was to try to solve this guy the exact same way that we just did? If I was trying to, if this is matrix A, let's say we were trying to solve for an inverse the exact same way that I just showed you. What would we do? Good. We would make a matrix such that the multiplication would equal what? But in this case, it's a 3 by 3 identity, right? So then I'd leading diagonal of 1s and 0s everywhere else. But how big would this guy need to be? A 3 by 3. So to find our inverse, wouldn't this be a bit more complicated? Can you guys tell why? Oh dear. Well, don't worry, the I is not an imaginary number, it's just a silly variable. But do you see what would happen if I started multiplying cross down? I would get 1a plus 3d minus 1g equals 1. Oh no. And then I could keep on going to the next and then to the next. I would have 2 other equations and then I would start over again with 2a plus 7d plus 5g. I'm not even showing the other ones. I'm literally just showing the a, d's, and g's equaling 0. And then 0a plus 4d plus 1g is equal to 0. Guys, do you see how big our systems are going to get? Instead of 2 by 2s, or instead of 2 equations, 2 unknowns, now I have 3 equations, 3 unknowns. Now, have we done this before? Yes, but this wouldn't be the only equation to solve. Isn't that just for the first column? Or sorry, the first row? First column? What would I have over here and over here? 2 more. Ugh. Yeah, I agree. I agree with the looks of like, no, you got to be kidding. So is this a very smart way to solve for an inverse of a 3 by 3? No. No. So why am I showing you another way to solve for an inverse of an easy guy, a 2 by 2? Because this way might be a whole lot easier than that way for anything bigger than a 2 by 2. Does that make sense? No. Is this ridiculously hard for a 2 by 2? No. Because our systems were nice and easy and a quick elimination and we're done. Well, back substitute. But that would not be quite so easy, and especially if I had 3 of them. Ugh. So let's talk about how systems of equations were made easier in section 8.1 and 7.3. Row reducing. What do you see? Another way to solve for an inverse that might be helpful for big guys is to take your original, to take your inverse, still with this identity statement or this definition, like, oh, a matrix times its inverse is the identity. That's true. But instead of actually multiplying and making systems of equations, which we don't want to do for anything bigger than a 2 by 2, we doubly augment. We take both of these guys, and instead of having just one column that you're setting it up with, you have 2, or whatever size matrix the identity is, you're putting these 2 together, the coefficients and the identity together, and saying, all right, go from having A and I to having I and, ooh, we're going to use row reducing to undo A, which we always do with row reducing, RREF. We're trying to get the identity matrix and the solutions on this side, but in this case, if we undo matrix A to make it the identity, as we undo A, we are building up A inverse. It's kind of cool. The undoing of one side is the doing of the other. Interesting. We could go into like heroes and villains. The undoing of a hero might be the forming of a villain. But anyway, we won't go into all of that as far as the illusion. But the idea is if we put them side by side, as we undo the one, we will build the other. And at the end, if you can get the identity, you will have the inverse. And if it is impossible to get the identity, guess what is not possible to find? The inverse. So it'd be non-invertible or singular, impossible to be inverted. And if you guys want to think about a way to remember singular, remember that vocab from yesterday? Your calculator actually knows this vocab. If you try to find an inverse, we will learn how to do that before we're done today, so have your calculators out. But as we use our calculator to find our inverse, if it's not square, I think your calculator would say like non-square. What are you doing? Non-squares never work. However, if it's a square matrix whose inverse doesn't exist, your calculator will actually say singular as the definition or the description of the error. So it's nice that whoever coded your calculator knew the vocab as well. But singular, the inverse doesn't exist. So anyway, coming back to what we're doing, if row reducing can't get the identity, the inverse does not exist, the original matrix is not invertible, aka, using that vocab term, is singular. Way of remembering? Single, on his own, doesn't have an inverse. Oh, poor guy. Although I guess in some ways, if the hero doesn't have a villain, maybe that's nice. All right. So what do we do? Why am I giving you a 2x2 and not a 3x3? Because I'm making it nice and easy, but it can be applied to a 3x3 with a lot less frustration, aggravation, pain, and suffering than this method would be. Okay? So, what do? We say this guy times a matrix X, like a 2x2. We could write all the variables, but whatever. Needs to equal the identity. And we doubly augment. Say, okay, fine. We'll take all these coefficients, 4, -1, -3, 1. And not just augmenting with one column, but with two. And then we use basically our row operations from section 8.1 to undo the matrix on the left, but realizing whatever we do to one term, we have to do to the entire row all the way across. So guys, how do we get this guy towards the identity? Where do we start in work by columns? Column 1. We're dealing with the 4 because we need to make that a 1. So we work first, remember, by columns, getting the 1. So this second row, totally fine as is. We don't touch that second row until we don't touch the row with the 0 until we establish the 1. So guys, do you remember what row operation we use to get the 1? Divide by. So can I just divide by? Yeah? So go all the way across and double check my work. As I read it, let's see if we match up. I'm getting 1 and -1/4 and 1/4 and 0. You guys agree? Sweet. Do we have our 1? The answer is check. Yes, we do. Once we get the 1, you tell me what's our next objective in column 1. Get the 0. So leave row 1. We've already dealt with him. It's time to tackle row 2. Remind me, how do we get zeros? You could do subtraction. I like instead adding the opposite. So we add to row 2, and then Matthew's been saying over here, multiply. We're multiplying row 1, wherever your 1 is, by the opposite. So the opposite would be a +3, right? But then, Jason, when we add the 3 plus the -3, it will be some sense like a subtraction. Just be careful. Yeah, just be careful. Get a little bit ahead of me. It's been a while since we've done this, right? You have to multiply every term in row 1 by 3 and then add. Remember, if the mental math is a little too rough, you can get your scratch paper off to the side and write out the entire little equation and then bring it in. But mental mathers, 3 times 1 minus 3 was, in fact, 0, right? The next one you're not going to like, because it's 3 times -1/4, which is -3/4 plus 1. But can't we think of 1 as being 4/4? And 0, well, I think 0 is going to be easy, and 1 is 4/4. I'm doing that because we're going to have some maybe fractions, or maybe not. But -3/4 plus 4/4 is just +1/4. 3 times 0 is 0. No, I apologize. 3 times 1/4 is 3/4 plus 0. Then 3 times 0 plus 1. I guess I didn't need that 4/4 after all. Are we okay? I think we're good. Now it's time to go to column 2, yeah? Column 2, we have to figure out what row we're dealing with. Column 2, I need to establish my 1. Where should my 1 go? Row 2, good. So in row 2, I'm dealing with each of those elements, but row 1 I'm not touching. Go ahead, Joe, what's your question? There are creative ways of changing it up, but if you were coding a computer to do it the same, so I'm just following the system. But yeah, you're right, there are other ways. Just be careful. However, for our system, we would just say, no big deal, get the 1, and you get the 1 by dividing, or multiplying by the reciprocal. So I could just say 4 times row 2, if that makes it easier. 4 times 0 is 0, 4 times 1/4 is 1, 4 times 3/4 is 3, 4 times 1 is 4. Well, that's nice. All my fractions went away. 4 over 1, yeah. You're probably thinking 3/4 here. And once I establish my 1, how do I get zeros? Yeah, add the opposite, and to get the opposite, I need to multiply. Right? We're adding to row 1. Adding the opposite. Oh, and the opposite is positive 1/4, so 1/4 row 2 plus row 1. Does that make sense? Cool. Once again, you could write it off to the side, the little baby equation with each of the terms. But for my purposes, I'm going to go for it. 1/4 times 0 is 0 plus 1 is 1. Perfect. That'll never get messed up if you follow your system properly. Now 1/4 times 1 minus 1/4 is just 0. Perfect. Keep going. 1/4 times 3 is 3/4 plus 1/4. 4/4. Nice. And then 1/4 times 4 is 1, and 1 plus 0 is 1. Were we able to get the identity on the left? Yes. Have we undone matrix A? Yes. And as we undid matrix A, what was built, as long as you did these operations all the way across, what was built over here? A inverse is equal to what's left? 1, 1, 3, 4. And let's check Matthew's pattern that he saw last time and see if it still works. Look at your beginning matrix and look at your ending matrix, and what is the relationship, the patterns between them? Switch the main. Yep. Opposite, the opposite. Oh, that's my way of remembering it, sorry. Switch the main. Yep. Opposite, the opposite. Hey. Well, then why don't we just do that every time? It's almost a formula. It's almost the entire pattern for a 2 by 2. It's almost the entire pattern for a 2 by 2. But the problem is that pattern doesn't work for a 3 by 3. Remember I said there were tons of ways to do 2 by 2s? The pattern doesn't work for the 3 by 3. And once again, didn't I say that's almost the entire pattern for the 2 by 2? Do you guys see anything on this page that has to do with the pattern that we've been talking about? Here's A. Here's A inverse. And what do you notice? There is a formula. And is there a pattern like Matthew saw, where you switch the main and you opposite the opposite? Yes, but what else do you technically see? For both of our examples that we've just done, this beginning part was 1 over 1, so this was all that there was to it. But if this beginning part is not 1 over 1, guess what? This is part of it, but it won't be the entire final right answer. So go ahead and get the special formula down. We are going to see a matrix where using the pattern would not get you the final correct answer. Both the methods that we just solved with little matrix A and B and C and D will always get you straight to the inverse if it exists. The little one that we just saw with the double augmenting row reducing will always get you to the inverse if it exists. But the pattern that you guys saw, while it's helpful, while it's useful, gets you part way there. Sometimes all the way, if this is just 1, but sometimes only part way. So it's dangerous to only use that pattern. Sometimes you'll be right and sometimes you'll be wrong. If you want to see an example, I just need... Now, there is a pretty cool trick here at the bottom, and this is something I alluded to when I was like, when I make my example, I need to make sure the inverse actually exists for that one on the board. What do you notice right here at the very bottom of this little baby formula? Now, for right now, it's just 2 by 2s, and that was a 3 by 3, so I had to figure something out for how to apply this idea to a 3 by 3. That's actually our entire next section. Section 8.4 talks about who is this AD minus BC. I think he's someone important, and he totally is. He's kind of as important, to matrices as the dot product was to vectors. Remember the dot product was a special guy, and he was like this number, and then he was used in all these application formulas? It's kind of what the determinant is. Ooh, I just gave it away, but Matthew gave it away before me. What this guy is, the determinant, and how it's used for matrices. But we'll see that next section. Next section is let's go in depth on determinants. So for right now, just talking about 2 by 2s. If we were to do the pattern to this guy right away, and be like, oh, hey, the pattern's cool, makes everything easier. Switch the main, 2, 3, opposite the opposite, 1, 2. We're wrong. It's not the inverse. No, but it's the pattern, and we saw it twice, and it worked twice. Switch the main, opposite the opposite. I did it right, but it's wrong, and here's why it's wrong. If we were to do that whole ABCD thing, or if we were to do the doubly augment, it would not have gone down to this. Instead, what it would have gone down to, which would have been a little bit nasty, is 1/2, 1/4, 1/2, and 3/4. And you're like, it doesn't even look similar. Well, maybe it looks similar, because guys, isn't 1/2 2/4? What do you notice? It is 2, 1, 2, 3, but what are they all divided by? 4. Why are they divided by 4? Because there's this extra piece to the pattern, which sometimes is 1, so it just looks like this is the only thing that's happening, but we have 1 over, who is A times D? Isn't that multiplying the main A times D minus, take away, B times C? One silly way of remembering it for the determinant, AD minus BC, it's technically what we call a DET of matrix A. Don't worry. Remember I said next section we talk about this guy called the determinant a lot. But another way of remembering it for 2 by 2s is the main diagonal minus the opposite diagonal. I don't know. In my head, it's easy. Main minus opposite, and we're multiplying minus multiplying. But we could do that here, and multiplying, it'd be 2 times 3 minus, well, careful. I was using my wrong inverse. I need to use matrix A. So 3 times 2 minus -1 times -2 times, switch the main, opposite the opposite. I have a way of remembering that too. But what ends up happening when I do 6 minus +2? What do you get?
4.
1/4. And 1/4 goes distribute, 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 dun, 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 dun. So, what about that dude? Let's use the formula now that we've seen it. It's not quite as easy as those two with the patterns where it was just switch the main and opposite the opposite, or switch the main of the entries of the main and switch the sign of the entries of the opposite. But now we know a formula, so it's like, okay, cool. I like this idea because he looks a lot easier than either of the two methods. All right, so 1 over. Guys, who's my main? 6 minus. Who's my opposite? And then it's like, okay, switch the main, opposite the opposite, but what did you just, 1 over 0. Oh, that's right. A is invertible if and only if the determinant's not 0. So what's going to happen if the determinant is 0, or if you get 1 over 0? Well, you guys know what happens with 1 over 0. It's undefined, right? Yeah. So if it's undefined, the inverse doesn't exist. And if the inverse doesn't exist, guess what's true about B? Poor guy, he's singular. But we saw maybe that's not always bad. Well, at least with heroes and villains. So guess what I was checking when I was seeing whether or not my big ol' 3x3 actually had an inverse or not. Now, I wasn't doing main and opposite. Remember, we don't know how to do that with this. But what was the name of what couldn't be 0? The determinant. I know we haven't technically learned it yet, but the determinant. So what I was checking is his determinant 0? Because if his determinant is 0, even though he doesn't really have a formula like this formula is only good for 2x2s. But even though he doesn't have a formula like this, the same thing applies for any size matrix. If the determinant is 0, he can't be undone, which is kind of cool. You can think he has no Achilles heel if we're going along with the heroes thing. So determinant 0, he can't be undone. But if the determinant is anything other than 0, yep, he has an inverse. It can be found. There is a page right here. We've seen this a few times. You guys saw it in section 8.2. You saw it again in section 8.3. This whole, like, you have a matrix A times a variable matrix X equals a matrix. Well, hold on. But this one isn't A times X is I, so this isn't necessarily an inverse. So why are they bringing this in? A times X equals something random. Why are they bringing that in right now? Guys, if this was an algebra equation, instead of capital letters indicating matrices, if this was just like a little letter, A times X equals B, how would you solve for X? Divide. It's easy. The inverse of multiplication is division. Dun, 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 dun. So what do we do if there are matrices? Divide? Is division the inverse operation of multiplications of matrices? What is the inverse operation of multiplication of inverses, or of matrices? So guess the only legal way to solve for X as far as inverse, you would need to multiply the left by the inverse. And what you do to one side, you must do to the... But why am I writing it so weird? Wouldn't we normally just be like, whatever, times 2, times 2, times 4, times 4, divided by 4, divided by 4, whatever it is that we're trying to do? Why was I very particular about writing it right here and not over there? Matrix multiplication can't go both ways, right? So if you were to ever bring in a multiplication of a matrix for a purpose like undoing, if you write it on the left, which is what you have to do based on the placement, writing it on the left to undo A, guess where you have to put it on the other side? On the left. All because it's not like numbers where I can say 2 times 3 is 3 times 2, no big deal. Or times 3 on the left is times 3 on the right, no big deal. Matrices, not like that. But what would happen with an inverse times an original? Identity. Does that make sense? And if you have the identity times your variable matrix, and the identity times a matrix is just that same matrix, here's another way of solving a system without row reducing. If you can separate the coefficients from the variables with your answers over here, you can actually always find all the variables with one multiplication of the inverse of the original coefficient matrix times B. Why is that a big deal? Well, maybe in programming or in coding, maybe it would have been a whole lot easier to code, just find the inverse and multiply, instead of explaining to a computer all the row operations. And in computer programming, there's something called efficiency, the efficiency of a program. If you guys search in your app store for, I don't know, give me something that you might want an app to do. Scanner. Remember how I talked about I would love for you guys to, I would love for you even though most of you don't do it. 2, take pictures of your homework, make them PDFs before you post them in classroom. Okay. Couldn't you look in your app store for Scanner? Yeah. How many different Scanner apps will show up? Tons. Now, how do you judge based on which one you should try? Probably the price and probably the stars. Maybe the reviews, right? Yeah, but not all. But anyway, wouldn't you consider the price? Like, Joe, if there was a $9.99 one and a free one, wouldn't you try the free one first? Okay, so long story short, that's what you would consider. However, the efficiency of a program actually has to do with how many steps it takes. So all of those, now that one has like graphics, and like there are lots of different, making it user-friendly, making it not user-friendly, but just like going back to the basics, there are lots of different ways of programming that could lead to the end result being the same. But if this one has like 1,000,000 steps and this one has 10, guess which one's going to be faster? 10. Exactly. And don't all of us want things to be faster? Yes. Okay. And we've all dealt with either websites or web pages that are slow, and you're like, oh my goodness. Now there's the whole Wi-Fi connection. We won't start about that. But coming back, one other way of solving this system without putting it into a matrix and row reducing is just to say, hey, let's just make matrix A this guy of 0.2, negative 0.6, negative 1, and 1.4. And then we have our times x, which is your x and your y, equals b. You could say there's a times x equals b, which is 2.4, 0.8. Another way of solving for x and y without doing any row operations is say, hey, find A inverse and multiply it by your b. But then that begs the question, well, wait, if we're able to use our calculator for this, is there a way to do the inverse in the calculator without having to worry about all of the different procedures? Well, we could do the doubly augmented thing and then do RREF, but that's a lot of work to put in like the one matrix and the identity and then RREF. You guys ready? If you put a matrix A into your calculator, he better be square. If he's not square, there's not going to be an inverse, right? But if you put a matrix A into your calculator, for instance, like the one that's right here, this little baby 2 by 2. I want you guys to go to the home screen like we always do for matrices. If you were to put this guy in, go to the home screen once he's in. Get your name. Remember, we name matrix A. Put your name first, and all we want is an inverse. You could go to matrix math, but guess what? There's already an inverse operation. See underneath the math button, the -1? Hit the -1 and hit enter, and guess what your calculator will give you if it's possible? The inverse. So right underneath the math button, as soon as you name your matrix, the -1, enter, and there's, the end. Oh, gross, it's decimals. Math, frac, pretty fractions. Bye, guys. P.S. That was answering the final page of notes. How do you do it in your calculator? Bye.
You're welcome.